Okay, let's wait for people to join. This is very much a test live, so I just I'm trying out the portrait format more and doing more casual lives, just trying to see how this works out. I'm going to be avoiding the sun, this slither of sun, so we're going to see how that works out. Okay. Wonder what these buttons do. Oh, okay. We don't need to create a short yet. Hopefully you can hear me okay. Yeah, so welcome to the live. If you let me know where you're joining from, that would be brilliant. I hope I'm going to see... yes, I can see the chat. Hi, nice to see you. So, yeah, technically today is a CERN holiday. I did have some meetings this morning, and I've got a bit more to do, but otherwise, yeah, this is why I'm doing the test live, to see if this works out. Excellent. So I can see people in the chat. The numbers at the top for me aren't updating, but that's fine. I don't need to know that. So I'm not going to be here super long. I'm mostly just trying to see if this works. So do let me know if you have questions, and I'll try and answer as many as I can in the while. I'm sorry that this tripod is shaking. It's literally sat on my knee right now. I need to get all I have is like a mini tripod, and I need to get a bigger one for things like this. But I thought it'd be nicer to be outside and do the live from out here. Also, my microphone ran out of battery because I didn't plan this, so this is how spontaneous this live is. But I've been wanting to do more lives, so I wanted to try out this portrait format because then I know that more people get shown it on their mobile phones, so I thought that would be a good thing to test. So you see we've got people from the US, people from India, so welcome. Thanks so much for joining. Already got more enthusiasm for doing more lives. Great. Somebody from Germany. Nice to see you. Yeah, so let me know if you have any questions. We can just talk about whatever. It's a beautiful sunny day, but as usual, I hide in the shade because it's also too hot here. It's May, and I'm sat in the shade, and I'm already too warm because I'm not used to the heat. There's people from Sweden, from Israel, from Ireland, from another from the US. Welcome. An Italian living in Ireland. Oh, very nice. So hopefully it's as nice wherever you are. So yeah, let me know if you have questions. When did you create your first cloud chamber? Oh, great question. So I mean, the cloud chamber itself is over 100 years old, almost 100 years old, I think. About 100 years old. I have to check up the original dates, but my first one I made at CERN about 10 years ago. So I used to do this is going to shake a lot, isn't it? Sorry, I'll try not to move too much. We used to have or maybe we still do, but I don't teach it anymore. So we have labs at the museum at CERN, and students and now visitors can come and build a cloud chamber themselves. So I used to be one of the instructors for this, and it's really simple to actually build one. You can essentially just take a fish tank, even a small fish tank, turn it upside down. You put felt on the inside top of the fish tank, which you soak with pure alcohol. And then at the bottom of the tank, you have a metal plate, and underneath that, you put dry ice. And so you should have about 100 degrees of temperature difference. And then this will create a super saturated cloud of this alcohol. And then what happens is when a charged particle passes through that cloud, it causes tiny droplets to form within the cloud, which you can then either see with your eyes, you can take a photograph of, which is a really cool way to see that particles are happening. Are particles that come from particles from space that hit our atmosphere and then spray particles down towards us. So these are mostly muons, the heavier cousins of electrons. So you can see these in the cloud chamber, which is really cool. And then you can also see there's a lot of radioactivity naturally around us everywhere. And you can see that in the cloud chamber as well. So you can see particles when they spontaneously emit other particles. And some of these are alpha particles, which is essentially like a helium without its electrons. And this causes like a nice little chunky track in your cloud chamber. So you can really look at the different paths of particles in the cloud chamber and work out which particles are going through just from how the different patterns they show. And this is essentially what we're doing in the Atlas experiment, but on a much, much grander scale, much more massive. We look at the way the tracks pass through our detector, and then we can work out which particles they were, we can work out what direction they came from, and then we reconstruct that to see what was happening in each of these collisions. And then there's a question about the heaviest antimatter particle discovered at CERN. And I should know this, and I can't look on my phone because I'm literally talking on my phone. It was recently announced, but I didn't read the article because I didn't work on the research. So we're going to try and pull it up now while we're talking, just so I can refresh my memory on that. Let me have a look at... So I'm very sorry if my colleagues who worked on that is watching this, but I saw the news and I didn't yet read it because I was busy with my own research. Okay, it's going to take me a minute to pull it up. I have to have a look, but that's a bit boring for you to watch me search for things. Any tips for students who'll be applying for the summer student program 2026? Yeah, so if you for the summer student program, for the ones for undergraduates, which is not the same as the student camps. I misspoke in my short video that I made advertising the Solvay summer camps, which is for high school students. The summer student program is for undergraduate students, and that will be next year. So the applications for that will open in about in around winter. And for that, my best advice that I can give you is just to make sure that you do your research about CERN and really think about what you would like to do as part of your summer student program. You don't have to know exactly, nobody knows exactly what they want to do or what programs are available, but the best advice is to really think, well, do I want to work on one of the particle detectors like Atlas or CMS or ALICE or LHCb? Do I want to work on the accelerator, in the accelerator group? Do I want to work in computing? Am I more of an engineer? Do I want to work in antimatter? And try and see what the different programs are. And you don't have to narrow yourself down too much, but the best thing that you can do is to show that you understand a little bit about what's happening at CERN and that you're going to make the most of this opportunity. And that really helps as well then when the supervisors are picking which students to assign to their projects. If somebody really does want to work on accelerator physics and they talk about why they're inspired by the different accelerators at CERN, that they want to work in accelerator physics, you are far more likely to then get put in the right project because the supervisors can see that you want to work with them. And then that would be my best advice for the summer student program, is just to make sure you're doing your research about what we're doing at CERN and to show potential supervisors that if they pick you, you're going to make the most of the opportunity. Nice. Somebody's wearing their Atlas experiment shirt that they've had. Somebody asked if they're from Switzerland and can they come and visit CERN soon. You can come and visit any day but Monday. So we're not open on Mondays, but we do free tours every single day at CERN. So you can just rock up and register for one of our free tours when you get here. I would recommend that you arrive in the morning, because some of the tours get instantly snapped up if there are lots of people arriving at once. And so if you arrive in the morning, you can prioritize registering yourself on a tour, and if it doesn't work out, you can go look around the museum, you can sit in the cafe, you enjoy the views of Mont Blanc, and then register again for the next round of tours. And that gives you multiple chances to get on one of our tours, and you can spend a couple of hours looking around our free museum, which has recently been done and is really exciting and shows you about quantum physics and how particle physics and CERN fits in the wider research that we're doing about how our universe works. So yeah, any day but Monday, you just turn up. It's all free except for the cake in the cafe and the coffee, obviously, but the museum and the tours are completely free. Let's have a look. So somebody's asking about book recommendations. So it's been on my list. I need to make a couple videos about that, because you're specifically asking for quantum physics and maths, and so I will dig some of those videos up, some of those books up, and let you know which ones I think are the best for reading about that. What I really recommend is to pick a couple of different books, because especially if you're reading pop science, then everybody has their different way of explaining things, and if you get it from multiple different people, then you're going to get a much more rounded overview of the explanations and the concepts. And then after that, you can start. If you read a lot of pop science books, then you can start to read some of the more, like, depending on your education level and how much you want to know, you could read some of the entry level textbooks if you really want to dig into the maths. But I don't necessarily, if you're just wanting to learn about the concepts and the big ideas, then I wouldn't recommend doing the textbooks. It depends what you want to work on. How many more years will you get to work at CERN? Because I heard that no one is really permanent there. Yeah, it really depends on the on the situation. There's so many different situations at CERN in terms of jobs. There are some people who work directly for CERN, and we have few permanent jobs in that situation, and it takes many, many years to work up to that position. We have a lot of PhD researchers and what we call postdoctoral researchers, who are really the ones doing the day-to-day research, and they're also getting trained by more senior staff, and I'm talking specifically about physics here. They then often, not everybody wants to be permanent at CERN. They want to do some years of training and working on the data. And then that's a really good lead in to other kinds of positions. I've got friends that went on to work in medical physics. They went on to work in finance, in consulting, in teaching, working for the government, doing advising on science and stuff like that. So not everybody who works at CERN wants to be permanent. They want to get the training on AI, on big data, on simulations and maths and logic and all of the things that we're teaching at CERN, and then they go and apply that in different fields. But there are people that do really want to be permanent at CERN or in particle physics, and I will say it can be difficult to get a permanent position. It's not super simple because we have more people doing research than we have permanent positions, and this is a general academic thing that we need to be working on. I am very fortunate that I have been working at CERN already for over 15 years, and I have a permanent job with the University of Amsterdam, and I work with NICEF in the Netherlands, and my job is permanent. I also do teaching at the university, so I am a teaching and research academic. So I spend about half my time teaching at the university and half of my time doing research at CERN. And so I split my time between Amsterdam and Geneva, depending on where I'm focusing most of my efforts at that point. And then I'm just always on social media, online, talking about physics. So for me, I'm very fortunate that I will get to work at CERN as long as I want, basically, because my research position in particle physics is permanent. And I love my job in the Netherlands and my team, and I'm really lucky that that worked out for me, because it's what I want to do with the rest of my career, is to do research and to share the knowledge that we gain from the research collectively. It's thousands of people, with new students and then with people more broadly, because our research is publicly funded, so therefore I want as many people to understand and learn about what we're doing as possible. Great. Higgs boson, any updates? So that's a good question. One of the interesting things I think about particle physics is, and the sort of public discussion about particle physics, is that you'll hear about the big updates, but we are constantly sort of chugging away at the research and the data. So we tend to collect the data in a few years sets. So we call them run 1, run 2, and run 3. And we're sort of 2/3 of the way through run 3 now. Our third run. We're going to run this year in 2025, and then we're also going to run a bit of 2026, and that will complete our run 3 data set. And then we analyze that data, and sometimes we'll put out new results halfway through, and sometimes we'll wait until the end of the run to put out a new result, because we've got to collect years worth of collision data to be able to sift through it all. And then on top of that, we will combine it with previous years of data to get even more statistics. So for the very rare things that we're looking for, we can then collect 10 years, 15 years of data, and combine it all together and sift through all of the different particles and events that we've created in the collisions and collected. And so it can take many, many years for new results to come out. We are still working on the Higgs boson. We're doing a lot of what we call precision studies, because now that we've discovered it, we want to test every single property against what the theorists predict. Just to it's always good to verify whether or not the predictions are true, and B, we want to see if there are any differences between what the theorists predict and what we see, because that's where things like dark matter could show itself within our collisions. So when we're looking for things like dark matter, we are looking for bumps in our data, like we did with the Higgs boson, and say there's a new particle, that's very exciting. But we're also looking for points where there's just slight, tiny differences. In the same way, the best analogy that I have heard, scientific analogy, is that when astronomers were studying the stars, they saw tiny, tiny differences in where some of the planets were compared to the predictions according to the gravitational calculations that they'd done, and just the calculations of the movements of where the planets were in the sky. And they predicted a new planet, which ended up being Neptune. And they looked exactly where they thought this new planet would be, and they found Neptune. And this is exactly the same thing that we're doing in collider physics, is that we're looking at all the particles we know about and measuring them to really exquisite tiny details, and then seeing if there is any difference between the prediction and the measurement, and that could help us find things like dark matter, just like Neptune was found. Somebody's asking, I think I heard that there will be an even bigger collider. True, will you be there? So this is a really big discussion right now, and something I'm going to make some longer videos on to explain what's going on. But also, if you happen to find my colleague Freya Bleckman, she's been doing a lot of videos as well about the process of choosing a new collider, because it's not decided yet. This is a multi-year long process to decide if we want a new collider, and then which new collider it will be. So the Large Hadron Collider will be getting an upgrade. At the end of next year or middle of next year, we start building we already started building it, but then we go into full build mode. And we call it the high luminosity LHC. And luminosity is basically how much data we get every time the particles collide. So it's going to be an even more efficient machine. And that's going to run until about 2041 is the plan for the HLLHC. And then after that, we turn it off. And so we're discussing right now, what do we want to do after the HLLHC has finished its programmed lifetime? And this is a process with thousands of scientists from all over the world we've recently just completed something as part of the European strategy review, because CERN is in Europe. Other regions also have their own strategy reviews or discussions, and then a lot of countries outside of Europe also input their opinions into the European strategy review, which then goes to CERN and the CERN Council to look at. And there have been proposals that are very strong proposals for multiple different collider options. One of the front runners that is getting a lot of media attention is called the FCC, the Future Circular Collider, and this would be a 91-kilometer collider compared to the LHC's 27-kilometer long collider. But it's not been decided yet. There's we have to do feasibility studies. We have to do very big discussions about what all the physicists want to focus on. What are people interested in studying? What is feasible with each different kind of collider? What is feasible to build? What kind of technology does it need? All of these things have to be discussed so that we can make the best choice for the future of particle physics. And there's going to be a symposium for physicists in June, where a lot of all of this input is going to be discussed with many physicists, both in person and online, so thousands of physicists, to discuss what the right option is. So it's basically, the plan is still ongoing. There's a lot of discussion about the different options, because you also need to you need to see whether you can do it before you decide that you will. And so then we have to look into a lot of things. And it's a very open process. A lot of people get to put their opinions forward and discuss scientifically what is the best. Also globally, because CERN is a global physics laboratory. So it's not. Basically, the short answer is it's not been decided yet, but it's a really deep, ongoing process that everybody is involved in at the moment. There's a question: why did I choose the top quark? The top quark is very interesting. It's one of the what we call the fundamental particles in the Standard Model. Um, it's like the Higgs boson is also a fundamental particle, but it's a quark, not a boson. So bosons are associated, most of them, with the forces in our universe, and quarks are like the stuff, the things that things are made of. So, for example, the protons and neutrons inside you and me are made of an up quarks and down quarks. I think a bug just fell out of my hair. Um, and top quarks are like the heavier version of an up quark. And because they're so heavy, they interact with the Higgs boson very strongly, which can help tell us more about the Higgs boson. And they also change very quickly into mostly bottom quarks and W bosons. And so we can look at then the process of it. We call it like a bare quark because it changes before it has time to buddy up, although that is an interesting phrase that I potentially won't be saying for much longer because we're doing a lot of studies into that. And so it's just a really interesting quark that interacts with a lot of other particles and allows us to do multiple studies at once. It tells us about potentially the lifetime of the universe because it's involved with, again, with the Higgs boson. It can tell us whether we live in what's called a stable universe, a metastable universe, or an unstable universe. And this is linked to the Higgs boson, and I have to show you diagrams about the potential for the Higgs boson. But if you ever hear that, like, Stephen Hawking said that the Higgs boson would destroy the universe, that's not what he said. The Higgs field and the potential could lead to the destruction of the universe in billions of years, so we don't have to worry about it. But it's not something that at CERN, for example, we can have any effect on. It's just something we're measuring to kind of find out more about it. Anyway, there's a fun existential crisis for you for this Thursday afternoon. Somebody says thanks for the superpowers. You're welcome. I didn't get any, so I don't know how you managed to get some. Um, if CERN discovered a link between worlds, then I'm your best feedback in data. Okay, thanks. How much is AI influencing changing the research at CERN? Oh, I love this question because, again, I've been meaning to make more videos about this. I've been using machine learning, which is basically what AI is, for 15 years. I did my master's research project on it way back when. We have been using machine learning in particle physics and leading, so not directly leading because there's machine learning researchers who are really doing the sort of the really leading the way, but we've been directly involved in implementation and feedback on improving machine learning for 20 years because we get a lot of big data at CERN that we have to sift through all of the information. And machine learning is basically algorithms that you can apply in a way to choose which data to keep, which data to reject, how to better understand your data. And so we've been using it for a very long time. And it was really interesting to me that when I started, a lot of physicists were against using it. They called it a black box, that you don't really know what's going on under the hood. And now it's significantly more popular, but we see it also being more popular everywhere. But yeah, we've been implementing many different types of machine learning, which we would now maybe, often publicly call AI, in our research for a very long time. So yeah, when you say how has it been changing, it really has. Also, the improvements in machine learning have been improving the way that we can search through these massive data sets that we have. And we're using it for things like anomaly detection, which is if you've ever had a phone call from your bank where they've said, hey, we've noticed some weird charges on your account, we just want to talk through those with you. That is not some person sifting through all your data and going, oh, they've spent a lot of money at this clothing shop, maybe that's weird, we should give them a call. That is anomaly detection algorithms looking for patterns in your data and what's normal for you, and then they see this abnormal, unusual purchase, and that gets flagged by the algorithm that then triggers the bank to call you and say, this is weird, was this really you? Which is very useful because you don't want fraud or people to use your credit cards, right? And we can use the same algorithms in particle physics to train it on the regular particles in the standard model and say, hey, this is what we're usually looking at, but we're looking for anything different that's happening, any new particles, dark matter, or something else showing up in our data. And yeah, basically, please just give us a little alert if you see anything weird. And I say weird, not in a super weird way, but like just different, that we can then investigate further. And there's so it's a different way of looking for dark matter in our data. Um, yeah. And somebody says, thank you for your answer. I also want to become a STEM influencer like you. Any tips on that? I'm in my third year of my undergraduate. I mean, I basically learned everything to do with being online and on social media by doing, and then reflecting on how my videos affected people, I haven't had any coffee today, but like how people appreciated them. Were they getting watched? Were they getting questions? Did people understand what I was saying? And so I just recommend trying it out and being very patient and very, yeah. Also, you can experience negative comments on the internet, and I wouldn't take that to heart because it can be a cruel place to be online. And the best thing is just really focus on the positives, focus on what you want to do. Why do you want to be a STEM influencer? Is there a community that you want to reach that other people aren't reaching? You think you can do it better? And honestly, you can. There are groups. Everybody has their own background and their own experience, so they can connect with people in different ways. So who do you want to reach? Why do you want to be a STEM influencer? Why do you want to share whichever area of STEM that you want to share? And then really focus on that, focus on the positives, focus on learning. And generally I try and pick up a new skill each video or try something new each time, and then be a scientist, analyze your data, see what works, see what feedback you get, and then that's the best way to grow. And nobody's perfect from the beginning. If you feel like it, you can scroll back on my previous stuff, and some of it's super cringeworthy, and I watch it now and go, oh, I wouldn't do it like that anymore. But I had fun as I was learning how to share physics. And that's really important too if you're going to be giving your free time, because nobody is getting paid at the beginning, just to warn you. I basically don't get paid now to do this. I get a tiny, tiny, tiny bit of money, and I'm talking pennies. But I'm not very good at like monetizing this because I have a full-time job. So my focus is on sharing physics with everybody. So if you're focusing on the money, you really have to think of different tactics. And basically be more organized than I am. But yeah, good luck, and make sure to connect with other STEM influencers. It's also about building community. It's about sharing and being really enthusiastic and cheering each other on, because this isn't a one-person show. I watch so many fantastic STEM influencers or scientists or mathematicians or people online, and I love what they do and I learn from what they're doing. And so it's really also about building community. Thanks. Somebody said everyone click on the like button. I really appreciate that. This is really a test. This is a very casual live. I've got no lighting, no nothing. My microphone, if you weren't here at the beginning, my microphone ran out of battery before I even started. But I just wanted to get started with the testing out this live and seeing if this is something I could do on a much more regular way. Oh, and a great question from Jimster saying, what's the number one physics question? I'm probably really behind on comments, by the way. I usually fall behind. What's the number one physics question you would like to see answered in your lifetime? I really want to know what dark matter is. That is the biggest question I have right now, is what is dark matter? Is it a particle? Are we creating it in our colliders? Can I study it? Can I work out more information about it? Or otherwise, if it's not a particle, what else is it? What is this big chunk of the universe that is having a gravitational effect, but otherwise very uninteractive otherwise? And I'd love to know what that is. That's the biggest question I'd love to have answered. Marjana says, I wrote a novel, part of which is set at CERN, and which one of the characters is inspired by you? But I didn't use your real name. Could I? It will be published in a few months. Maybe you can send me a DM on Instagram and we can talk about it, because it depends what your character does. I don't want a character assassination if they go off and have an evil streak. But yeah, maybe we could talk about it. I mean, first name's fine, absolutely. Full name, we'd have to chat about that. But I'm very honoured that I inspired a character. That is truly an honour. Uh, what is the typical? So David asks, what's a typical day like for you at CERN? My days, it's I keep meaning to make a video about this, and they are both very regular days and then also not so regular. It depends when. So I sometimes go off on tangents, so you will learn that if you attend a lot of my lives. My videos are highly edited. They're not highly edited, but they're at least thought about in advance. Um, my if you'd asked what my regular day looked like when I did my PhD, I would have been in a lab in a clean room or in our detector testing facility basically all day. That's what I did for my PhD. So I was testing new devices that are now installed in the Atlas detector, taking data. That we wanted to test how they could resist radiation, the radiation of the collisions going through them from the Large Hadron Collider after 10 years, 15 years of being in Atlas, to make sure that they could really last as long as possible, and that they wouldn't get so damaged that they wouldn't work anymore. So I was irradiating devices, I was testing them, I was like soldering things together. It was very hands-on. I worked with a team on the in the testing facility. Now I work much more on the data analysis coming from Atlas itself. So my day is kind of split up into three kind of things. I do a lot of programming to analyze the data and making histograms and doing statistical reconstructions of the data that we're doing. I do a lot of meetings, a lot of Zoom meetings and some in-person meetings, because physics is actually, people probably don't think this, but it's really interactive, especially at CERN. I'm talking to people all day. We're going for coffees, we're having meetings, we're talking about what we want to analyze, how we've analyzed it, what are our plans for the detector, all of that kind of stuff. And then the other main thing, and this is only on the research side, not on my teaching side, the other main thing that my day looks like is I do operations work. So I'm in the control room as part of the operations team to take the data when the LHC is running. Now I mostly do a shift called shift leader. So if you're a fan of Star Trek, I'm the one that sits in the middle saying make it so. But our control room is not as fancy as the bridge on Star Trek. But it's really a team effort. So we have the shifters in the control room. We do 8-hour shifts, and we are responsible for the Atlas detector during that 8-hour shift. And then we also have a whole team of experts around the world and also locally that we can call for absolutely any issue. So if any of the data looks slightly weird, or if one of the detector, the cooling isn't quite at the level it should be, we'll call an expert and they'll check on it. Or maybe one of the data acquisition racks needs resetting remotely or something like that. Anything, we've got a team of people who can be called at any single moment to make sure that we're as efficient as possible. And I really love the operations work. I feel like that is one of the key things that we can do in the Atlas collaboration to collect that data for then the thousands of scientists who are then going to analyze it, to look for things like Higgs bosons and stuff. So I'm either in the control room, not so much at the moment, but sometimes when I'm at the control room, I'm there for like the whole week. I'm in a lot of meetings all the time, or I'm sitting at my computer analyzing data, making plots, and doing coding a lot of the time. I'm not a good coder. I'm an adequate coder, which is, I think, says for a lot of physicists. I get it done, but I don't let computer scientists look at my code, because I used to live with one and he had a lot of comments about my code, and it gets the job done. It doesn't have to be the best, but I am actually starting a project right now to improve the efficiency of our code, so I'm having to learn a lot more proper techniques to make sure that when we run it on a CPU or a GPU, that it's actually very efficient, because then this is going to be run for like the simulation of Atlas, and that's a bigger project than me just making a few histograms on my computer. But the reason I bring this up is that people think that you have to be the very best at something to be able to do it, and sometimes you just got to be good enough, and good enough is fine to get the job done. And sure, you can learn more and you can improve, but you do not have to think you have to be an amazing genius to work on a project like this. You have to be curious, you have to be a patient, and you have to be able to ask for help when you need, and to talk to people about what you're working on. Um, Great. So again, I'm very, very far behind. Is CERN experimental data available online? Can we study it on our own and perhaps contribute something? You absolutely can study our data. If you search for CERN open data, then we have a portal. When I mean portal, as in a website, where you can go and download some of the data from one of the different experiments, and some of them have pre-written scripts that help you to sort of get started if you're really new. If you're a computer programmer or a physicist already, you can download that data and take a look at it and learn about what we're doing at CERN. So yeah, the CERN open data portal is where you can get open data from CERN. Do they worship Lord Shiva? Some people do. At CERN, we have a statue that was a gift from India. And when I say some people do, I mean globally. At CERN, no, it is a beautiful gift from the Indian government that is one piece of artwork that we have at CERN. Have I ever witnessed any supernatural activities or beings? I have not. Never at CERN, and I've never heard anyone who has said that they have witnessed any of this either at CERN, and I know thousands of people at CERN. Somebody says, good afternoon, Clara, how are you doing today? Very well, thank you. I am hiding from the sunshine in the shade, and at some point the live is going to stop when the sunshine gets to me because it's getting too hot outside. But otherwise, very good. Thank you very much. Any better magnets so you don't need a larger diameter ring? Great. That's a great question, because when I was talking earlier about building a larger collider, the reason that we would want to build a larger collider in the first place is because right now with the Large Hadron Collider, the limit on the energy for the collisions that we do is on the magnet strength that we have. And if we have stronger magnets, we can go to higher energy in the same ring for hadrons. The limit for leptons, which is like an electron, which is what we previously had in the tunnel for the LHC, is not on the magnet technology. It's on the fact that we lose energy every time the electrons have to change direction, every time they change path. And for that, if you just build a bigger tunnel, then the path is less extreme, and therefore they lose less energy going round. So if you want to have an electron-positron collider, you build a bigger tunnel so that they don't lose energy as much when they go around in a circle. And if you want to build a hadron collider, like with protons, you build a bigger tunnel because you then don't need quite as strong magnets to go up in higher energy. And if you get higher magnets as well, then you can go even higher energy just from combining the two. So this is what we're talking about, because it's very, like, what we did before is we built a tunnel at CERN, we put the Large Electron-Positron Collider, the LEP collider, in that tunnel, collided that for a while, did lots of very precision studies, and then we took that collider out and we put the LHC in the same tunnel. So we reused the same facilities that we had built to go first for a lepton collider and then a proton collider. And the reason that the lepton collider, we often talk about it being a precision machine, is because electrons are what we call fundamental particles. They can't be broken up into smaller pieces, and therefore you know exactly what energy you're colliding with, which is really, really useful and not as messy as protons, which have 3 quarks inside of them, a bunch of gluons, a bunch of extra quarks, and you're just smashing these things together, and you know what energy the proton has, but you have no idea which thing inside the proton collide. Well, we know, we can work out whether it was gluons or quarks, but we don't know how much energy exactly they had. And so we get a whole spectrum of potential energies for the collision, which is great when you're searching for new particles and you don't know exactly what energy you need to hit to make a new particle. But it also means that all of those other particles that didn't get involved in the collision can get sprayed off into other things, and it's much messier. It makes our job more difficult. It's partly why when I very briefly mentioned the simulation work, that's what I'm trying to like resolve or help better understand for our studies, or better model for our studies, let's say. And it's just very messy and very busy. So that's, yeah, bigger magnets, stronger magnets would mean that we could have the same tunnel and go to higher energies. There are also different proposals for a future collider. So a linear collider means that then if you're using leptons, like electrons or positrons, you're not changing direction. So therefore you're not losing energy if you're going in a straight line. So there's lots of different proposals. So there's also a question about what's the estimated cost to build this proposed new collider. Um, it depends on which collider you're talking about. I'm not going to give you an exact number now because the new data just came out as part of the European strategy, and I would have to look it up to make sure I gave you the right number because I do not want to misrepresent. It is in the order of billions of dollars or euros, or whichever currency you like. But this would be spread across at least around 20 countries internationally over 20 years. And so, generally, right now, what the CERN itself costs member state taxpayers is 1 cup of coffee a year, is how much it costs. And for 1 cup of coffee a year each, you get things like, so the World Wide Web was invented a long time ago, but this is something that was invented at CERN and then released for free globally. We get medical technology that comes from the kinds of research that we do. So, hadron therapy. So, I use the word hadrons a lot because the protons in the LHC. Hadron therapy is a new form of cancer treatment that uses the fact that hadrons give a much more precise energy deposit in the human body than, say, X rays do. And then this allows us to more precisely target cancer tumors and therefore reduce the amount of damage in healthy tissue. There's PET scanners that use positron emission tomography, so antimatter, in order to look inside the human body, including things like the brain. There's the first 3D X-rays came from CERN technology. So this isn't stuff that like people like me directly work on, but our research then feeds into, we're like the base layer of knowledge that then everything else gets built up on top of. Even maybe decades later, but we're building that foundational understanding of how the universe works. What are the particles? What are the forces? How do they interact? What technology can you use to search for these kind of things? And then on top of that, you also get the fact that I briefly alluded to it at the beginning of the video, we have thousands of scientists that come and work at CERN, and engineers and technicians and computer scientists and everything else who come and work at CERN for a little bit, get really trained, and then go off into other types of careers. And so one of the actual biggest cost benefits of CERN, according to some studies that I've read, is the training of people who then go back to their countries and then share that knowledge of how does AI work? How do you analyze big data? How do you how do you understand statistically what all this big data means? And then technically, how does all of this technology work? And then they go off and work in different industries. They do startups, they work in finance, they work in medicine. And so then this feeds back into the economy and just the general, I mean, economy is important, it really affects people's lives, but in my opinion, just a better informed society, a better trained and educated society that then benefits all of us is what we should be wanting in society. That's my opinion. Okay. What is the ratio of radioactivity that is processed during testing if not, is it mostly biotechnology? I'm afraid I don't fully understand the question, but there's radioactivity from the collisions that happen at CERN, and that mostly gets absorbed into the rock and into the detectors and stuff, and then eventually it just evaporates away in the way that radioactivity can do depending on the type. I don't know if I fully understand the question. Sorry. Somebody says they want to make a 3D LHC 3D model. That sounds very cool. Yeah, somebody says that they were looking at machine learning and neural networks as part of their computer science degree in the early 90s. Yeah, so it's been a while. I think I'm really far behind on comments, so I might have to jump ahead a little bit. One question, is it true that Google Quantum PC become nearly something really... Yeah, somebody's asking whether the Google Quantum PC became, like, consciousness. I'm gonna say no, because we use the word AI all the time, but we're not close to real AI yet. the everything that you hear that says AI, it's machine learning, and these algorithms are quite specifically designed for things still. They're getting better at doing more general tasks, but they're not really intelligent. They're trained. This is my opinion before any AI enthusiasts come for me. It's my scientific opinion. Um, so I would have heard more if the Google Quantum PC was clear. And I will be honest, there's a lot of hype around things that needs to be independently verified. As everything in science, all of my research is independently verified by other researchers. So until I hear a lot more independent verification of stuff, then I'm always very cautious when I read something. Um, there's a question: do you guys utilize antimatter to pull other particles? We don't use it to pull other particles, but we use antimatter all the time. So we used it in our previous accelerator, the LEP. It was electrons and positrons are the antimatter counterparts of electrons, and we were using those to collide together, and then they annihilate, and then you can create new things. We have an antimatter factory at CERN, which is very cool. So then we create antimatter as part of the collisions, and then we can take that and produce anti-hydrogen. So this is an anti-proton and an anti-electron, a positron. And we can study how antimatter works. This sun is creeping up on me, so I'm going to have to stop soonish. So yeah, we use antimatter all the time, but not to pull in the way that you think, like magnetically. Somebody's asking, can we make black holes? No. We have never observed micro black holes, and we know that we can't make macro black holes. The collisions that we do at CERN are exactly the same as the collisions that are happening in our atmosphere, because it's protons hitting other protons. And in our atmosphere, it's happening at much higher energies, and it has been for billions of years. And we have never, our planet has not been sucked into a black hole, although sucking into black holes is not quite the right terminology, but has not been absorbed into a black hole ever, as we can observe by still being here. And so the fact that for billions of years protons at higher energies have been colliding on our atmosphere tells us that we will not create black holes in our collisions. There was a proposal that micro black holes could be produced, which would then fizzle out, so they wouldn't stay. And we have searched for those, and they have not been shown up in the data. So there's no black holes created in our collisions. Somebody's asking, do you guys utilize any plant life to understand how different particles react to different objects and non-objects? We don't do bio research, so we don't look at plants in our research. I have to hide that in the shade. So there's a very kind comment that you said that I'm an inspiration, and what if somebody wanted to do exactly what I do, can you suggest a potential path to it? So the best thing, I mean, if you want to do my kind of path, I'm a particle physicist. I did an undergraduate master's degree, but the general way to do it is to do an undergraduate bachelor's degree in physics, a master's degree in physics where you specialize in particle physics, and this would be the best time, if you haven't already, to do an internship to do your master's thesis on a particle physics project. So find a university that can give you that research opportunity. During your undergraduate degree, you should apply to the CERN summer student program for undergraduates. I didn't do this, and I still managed to make it at CERN, but it is a great opportunity, and you should 100% apply when the applications for that opens in the winter. And then you should look to do your research at a university that can send you to CERN on either one of the LHC experiments, or there's multiple like really interesting particle and astroparticle research projects around the world, and that will give you the experience you need to then continue in this research area if you want to do it. So it's really about choosing the where you do your bachelor's research. You just want to have a great physics education. It's when you want to start doing your master's that you need to find a university that can give you real research experience. Thank you for the nice comments in the chat. I'm going to try and catch up because I am going to have to stop soon because the sun is creeping up on me. Saw a comment about vertical lives. Yeah, that's why I'm testing them. Let's see how this is going afterwards. Somebody saying shift leader woohoo. Yeah, this is how far behind I am. Sorry, I'm gonna have to jump ahead, so I'm sorry if I miss your comment. because I can see comments about stuff I talked about 20 minutes ago. Um, is there an edge to the universe? Like where space stops and you can't go any further? We don't know. I think. I don't know that. I'm not an astrophysicist, so I'm not the best person to ask. As far as I understand, there is no edge to space, um, and you can't go any further. But also, yeah, I would have to read up on the most recent data, to be honest. I'm a particle physicist. I only care about what's happening locally and then the cosmological implications of that. I don't say only care. I mean, I keep up to date with the research. As far as I understand, there is no edge to space, but I am not the best person to ask about that because I don't research on it directly. Um, so the comment Ghostbusters wasn't a documentary. Apology if that shatters anyone's illusions. Yeah, and a comment about redheads and the sun. Redheads shun the sun. I mean, it's true. I will get sunburn if I sit in the sun. So I've learned that. As a teenager, I used to think my friends used to call me a day walker, which was a joke from South Park because I did go like be more out in the sun. And I said I can handle it. And as I have matured, I've been made aware that it doesn't like it's not a good idea. Particles, like photons from the sun, can damage us if not treated with respect. So I treat all radiation with the respect it deserves. And it's all about minimizing your exposure. As a radiation trained officer, I follow the ALARA principles, which is as low as reasonably achievable. Which does not mean zero. So it doesn't mean I don't enjoy being around the sunshine, but I also don't sit directly in it if I have a choice, because there's no point getting burnt if I don't have to. Okay, we are coming up on the hour already, which is amazing. I was just planning to do a quick 20-minute live, and we've already done 50 minutes, so that's fantastic. And that is mainly because of the fantastic and amazing questions that you have all posted in the chat. So I've loved that. Thank you so much for joining me. There's a question, do you know if there are dimensions that can be exposed by warping space-time? I heard it goes up to 10 dimensions. Is it true? I'm a radiation... Yeah, you're a radiation officer. Yes, I am officially trained as a radiation officer as part of my research because I work with radiation both in my day-to-day research at CERN and also in my teaching lab. I teach particle physics, and particles are radiation. Everything has, there's radiation everywhere. And so I'm a trained radiation officer. So the question, multiple dimensions. So there are proposed theories, such as string theory, that proposes multiple dimensions, and there are different ways that this would then affect how the universe forms and exists. And it can go up to 11 for some of the ones I've read. And these would be not dimensions in the fun way that we see in Marvel, where you have a variant and you go visit your other dimensions and other possible ways that your life could have lived, which is super fascinating and to the realm of sci-fi. Dimensions are like spatial or time dimensions, and they are tied up microscopic most of the time, so we don't experience them. And the best analogy I've seen is that if you're an ant walking on a rod, then you only experience you only experience two dimensions, forward and backwards and around the rod, and they're not aware of the third dimension. If I messed up this analogy, anyway, basically as an ant walking on a thing, and they don't always experience all the dimensions, and so that could be how it is for us, that there are other dimensions in our universe that we just don't experience day to day in our lives. And there are these theories, and it could be that I'm not explaining this very well, it's because it's too hot. They could exist in our universe, but the main sort of problem for me as an experimental physicist is that we don't have a great way to verify if this is the truth. We need, as an experimental physicist, I need something I can test in my collider to see whether this is the way that the world works, or whether it's very fancy, interesting mathematics, but it's not actually the way that the universe works. So I'm very much an experimental physicist. I need something I can test and I can verify in my experiment. And at the moment, that's one of the places that we're struggling, is to have something really verifiable for this. Oh, yeah. Oh, thanks. Jimster says, don't forget to click the like button and subscribe. I appreciate it. Thank you so much for doing that reminder. I'm terrible at that, at asking people. If you happen to not be subscribed and you're watching this video, please do subscribe. And I make shorts and also working on more long form videos about particle physics and CERN. Thanks so much for the reminder to do the shout out. Don't put your hand in the beam. Yeah, that's basically radiation safety officer 101. Don't put your hand in front of the radiation. You can't do it at CERN because we have so much security to even get down to the tunnel. You can't get down to the tunnel when it's running, and there's a vacuum, so you couldn't get anywhere near the LHC beam when it's running at any point. Oh wow, somebody's joining from Mongolia. Nice to have you here. Yeah, so one last question that said, what role does quantum computing and quantum information play in work at CERN, if any? So quantum information, quantum plays a massive role. It's really deeply tied into our theory, our theories and our physics. Quantum computing, there's a very big B. Quantum computing is not something that we directly use at CERN, but that we are looking, there are people studying how we could use it better, because we use a lot of simulations at CERN where we're wanting to, the sun is like already hitting my arm, so I'm gonna have to sit like I'm shying away from it. I made shade. We use quantum computing, or we're researching quantum computing to see how we, oh sorry, I get distracted. We want to do our simulations at CERN, and it takes a lot of computing power to do these simulations, to recreate and calculate all of the different processes that are happening in those collisions of the protons inside the Large Hadron Collider. And if we had something like quantum computing, it just speeds up these kind of simulations significantly. And it would be, and the more simulations we have, the more statistics we have on the predictions, the better our predictions are, the better we can compare to the statistics that we have in data. Basically, the two best ways we can improve our results is collecting more data statistics wise, and then doing better calculations and simulations to compare it to. And so quantum computing would really improve our ability to do our predictions and our simulations for our studies. And to reconstruct the data. If we can, processing the data that's coming from the collisions, we have to have a lot of computing power for that. And so having quantum computers would also really improve the data reconstruction that we have at CERN as well. Okay, thank you so much for joining me. Thank you for all of the excellent questions. I really do appreciate it. Alara, good name for a safety officer then. It would be a pretty name. It means as low as reasonably achievable. It's very nearly my name. Yeah, thank you so much for joining me. It is now up on the hour, so I'm gonna sign off in a moment. I really appreciate all of the questions. I appreciate you joining, and yeah, thanks so much for making this so entertaining and fun. And I will do more of these. I will do some lives like this where we just hang out, and hopefully I'll start a bit earlier so that the sun doesn't attack me. And I will do more where they're a bit more structured and plan some questions in advance. And I would definitely do more tours when I can. When the LHC is running, we can't go underground, but there are many excellent places we can go above ground at CERN. And now that I'm based here at the moment, I will go and find some fun places for us to go and take a look at CERN and do some live tours there. And also my colleagues, there are thousands of other people who work at CERN. It's definitely not just me, all with different expertise and experiences. And I will try and find as many of them as possible to be in videos and to be in live streams, and just to, so you can talk to as many people as possible and learn about what we're doing at CERN. Because I think one of the biggest misconceptions about CERN is that we are closed and that it's secret, and that is 100% not true. Our papers are publicly posted online for free, so they're not behind any paywalls, and all of our research, because it's publicly funded, is we try and share it with the public as much as possible, and we are are open and we want you to learn about what we're doing because we love what we're doing, and so we want to share it with you. So again, I'm really happy that you came and joined me on this live. Thank you for the excellent questions, and I will see you in the next one. So have a great day or evening or morning or wherever you are, and take care and chat to you soon. Bye. Now I have to find where the off button is. This one.